A sealed door grinds open, and dry air slips out of a chamber that has not felt a living breath for thousands of years. Inside, there is dust, stone, painted walls, the faint geometry of offerings arranged for another world. Clay jars sit in the quiet like they are still waiting to be used. Some once held oils, some held grains, some held resins, wine, or fruit. And in the stories that travel farthest, one of them holds something stranger: honey, darkened by time, but still recognizable. Not a bone, not a tool, not a carving. Food. A food made by insects, stored by humans, sealed in a tomb, and still somehow not reduced to rot. That idea feels almost wrong. Empires collapse, languages disappear, wood decays, bread molds, meat spoils, fruit collapses into sugar, alcohol, acid, and finally nothing we would call food. Time seems to win against anything edible. And yet, honey has a reputation for refusing the ordinary rules. The famous version of the story says that archaeologists opened ancient Egyptian tombs and found pots of honey more than 3,000 years old, still edible. It is a powerful image, someone lifting a lid after millennia and finding sweetness waiting in the dark. But that exact claim needs care. Ancient honey and honey residues really have been found in Egyptian contexts. Tombs were often dry, sealed places where organic material could survive in remarkable ways. But the neat phrase, 3,000-year-old honey, still edible, is repeated far more confidently than many of the specific sources behind it allow. The legend may be exaggerated, the chemistry is not. Because honey is not simply a sweet liquid that happens to last a long time. It is a hostile environment disguised as food. To us, it tastes rich, floral, golden, soft. To most bacteria, yeasts, and molds, properly ripened honey is a trap. Too dry in the way that matters, too sugary, too acidic, and chemically active in ways that make growth difficult. That is the first turn in the story. Food does not spoil just because time passes. Food spoils because microbes can live in it. They need water they can actually use. They need conditions their cells can tolerate. They need enough freedom to grow, divide, and transform the food around them. Honey denies them that freedom, and it does not become that way by accident. Bees begin with nectar, a watery reward produced by flowers. Nectar is not immortal. It is not shelf-stable. It can ferment. It can feed microbes. It is much closer to a fragile plant syrup than to the thick substance stored in a jar. The bees change it. They collect it, pass it mouth to mouth, expose it to enzymes, spread it thin, fan air across it, concentrate it, acidify it, and finally seal it away. What starts as floral liquid becomes a dense chemical preserve. The hive is not just a place where honey is stored, it is where honey is manufactured. So the real mystery is not whether honey is magical. It is how thousands of insects, working without glassware, thermometers, or written knowledge, turn a spoilable flower liquid into one of nature's most durable foods. And to understand why a spoonful of honey can outlast almost everything around it, the story has to begin before the jar, before the tomb, before the legend. It has to begin at the flower, with nectar that is not honey yet. A forager lands on a flower and draws up nectar, but what enters her honey stomach is not honey yet. It is a watery, unstable liquid, rich with sugars, but still vulnerable to fermentation and microbial growth. The honey stomach is separate from the stomach she uses to digest her own food, so the nectar is being carried like cargo. Back inside the hive, that cargo is passed to another bee, then another, mouth to mouth, in a chain of handling called trophallaxis. With each transfer, the liquid is not merely moved, it is processed. The first transformation is concentration. Nectar can contain a great deal of water, depending on the flower and the conditions outside. Finished honey usually settles near 17 or 18% water, though it varies. That missing water is one of the main reasons honey lasts. But the important idea is not just wetness, it is water activity. A jar of honey looks liquid. It pours, stretches, glows, and clings to a spoon. But to most microbes, it is almost dry. Water activity measures how much water is actually available for life to use. Honey commonly has a water activity around 0.5 to 0.6. Many bacteria need something closer to 0.90 or above to grow. So even though honey seems wet to a human hand, it is biologically parched to a bacterial cell. The sugar is the trap. Honey is mostly sugar, often around 80% by weight, especially fructose and glucose. In that concentrated syrup, osmosis pulls water out of microbial cells. A bacterium or yeast cell landing in honey faces an environment so sugar-rich that its own water wants to leave. The sweetness that makes honey desirable to us helps make it hostile to microscopic life. This does not mean honey is perfectly sterile. Some hardy yeasts and spores can survive in it. But survival is not the same as growth. Properly ripened honey usually prevents them from multiplying. If honey absorbs moisture from humid air, or if it is harvested too wet, that balance changes. Then osmophilic yeasts can begin to ferment it, producing bubbling, sourness, or alcoholic smells. Honey's long life depends on staying concentrated. But sugar is only the most visible layer. Honey is also acidic. Its pH commonly falls around 3.2 to 4.5, low enough to make many bacteria uncomfortable. One important acid is gluconic acid, and its amount varies with floral source, minerals, and handling. The acidity does not work alone. It reinforces the low water activity, adding another barrier to growth. Then there is the chemistry bees add themselves. From glands in their heads, honeybees contribute enzymes during nectar processing. One of the most important is glucose oxidase. Under the right conditions, it converts glucose into gluconic acid and hydrogen peroxide. In thick, undiluted honey, there is so little available water that enzyme activity is limited. But when honey is diluted, the reaction can become more active, producing low levels of hydrogen peroxide, an antimicrobial compound. Some honeys also contain other non-peroxide antimicrobial chemicals, depending on the plants the nectar came from. Inside the hive, all of this chemistry is paired with behavior. Bees spread nectar into thin films, move it between cells, and fan their wings to drive moisture out of the hive air. The comb becomes a drying room. Only when the honey is sufficiently ripened do workers cap the cell with wax, sealing the concentrated food away. Beekeepers watch moisture for the same reason, often using levels below about 18 to 20% as a sign that honey is ready to harvest. Even after that, honey can still change in ways that look suspicious but are harmless. Crystallization is not spoilage. Glucose is less soluble than fructose, so it can separate into tiny crystals, especially in honeys with higher glucose content or in cool storage. The honey may turn cloudy, thick, or grainy, but its chemistry has not failed. Gentle warming can often liquefy it again. This is why the tomb story is powerful, even when the viral version outruns the evidence. Ancient Egyptian jars and residues show that honey was present in tombs and offerings, and those tombs could be dry, sealed, protective environments. Whether anyone truly tasted 3,000-year-old honey is much harder to prove. But if honey stayed sealed, dry, acidic, and concentrated, time alone would not be enough to make it rot. A hand lifts a spoon from a jar, and the honey folds back on itself in a slow amber ribbon. Nothing about it looks engineered. It looks simple, almost ancient by nature. Sweetness gathered from flowers, thickened by bees, stored for later. But by now, that spoonful is no longer just a pleasant food. It is a layered defense system. At the beginning, the strange part seemed to be the legend. A clay jar in a sealed tomb, a substance inside still recognizable after kingdoms had risen and vanished. But the deeper surprise is that honey does not need a miracle to resist decay. It needs conditions. And bees create those conditions with astonishing precision. They begin with nectar that could have spoiled. They reduce its water until most microbes cannot use what remains. They concentrate sugars until cells that enter it are placed under osmotic stress. They lower the pH into an acidic range where many bacteria struggle. They add enzymes that can help produce gluconic acid and, when diluted, small amounts of hydrogen peroxide. They move the liquid through the hive, spread it thin, ventilate it with thousands of wing beats, then seal it under wax when it is ready. So honey's durability is not one trick. It is a stack of barriers. Low available water, high sugar, acidity, antimicrobial chemistry, protective storage. Remove one barrier, and honey becomes less invincible. Let it absorb enough moisture, and fermentation can begin. Harvest it before it is fully ripened, and yeasts may find their chance. Leave the jar open in humid air, and the ancient balance starts to change. But keep that balance intact, and honey becomes difficult for ordinary spoilage organisms to conquer. That is what the tomb story gets right, even when it becomes too neat in the retelling. The famous claim of 3,000-year-old honey being found and eaten is often repeated with more certainty than the evidence deserves. Archaeology can show preserved honey, residues, and the importance of honey in ancient Egyptian life. It can show tombs that were dry, sealed, and protective. It can show that honey was valued as food, medicine, offering, and ritual material. But the image of someone casually tasting a perfect jar from the deep past is harder to pin down. Still, correcting the myth does not make honey less remarkable. It makes it more remarkable. Because the real story is not that honey escapes chemistry. The real story is that honey survives because of chemistry. It lasts because bees transform a fragile floral liquid into something microbes mostly cannot live in. The tomb is not the source of the wonder. The hive is. Return to that sealed ancient jar in the dark. Imagine not just the hand that placed it there, but the work that came before it. Foragers crossing flowers under a hot sky. Workers exchanging nectar in the hive. Enzymes entering the liquid. Water leaving cell by cell. Air moving through comb. Wax closing over the finished store. Long before the jar was buried, thousands of bees had already built a food designed to resist decay. A spoonful of honey is therefore not just sweetness. It is preserved behavior. It is insect labor made chemical. It is a record of flowers, climate, hive air, bee enzymes, and time held in suspension. That is why honey feels so ordinary and so uncanny at once. It belongs on toast, in tea, in a kitchen cabinet. But it also belongs to deep time. In the right conditions, it can wait with a patience that outlasts wood, fruit, bread, and the people who sealed it away. The final lesson is quiet. Honey does not defeat time by being untouched by nature. It endures because nature, through bees, has already done the preservation work.